One of the most popular two-dimensional NMR experiment is the homonuclear correlation spectroscopy, or so-called COSY sequence. The method is used to identify spins which are coupled to each other. In other words, COSY tells you what proton is coupled to what proton. The two-dimensional spectrum that results from the COSY experiment shows the frequencies of a single isotope, which is most commonly hydrogen, along both axes. This is why it is called homonuclear, because on both axes you see the same isotope. Peaks along the diagonal are the projection of the one-dimensional spectrum. Cross-peak results from a phenomenon called magnetization transfer. A cross-peak indicates that the two nuclei at the given chemical shifts are coupled. Each coupling gives symmetrical cross-peaks on both sides of the diagonal. The spectrum provides an easy visual way to determine which protons are neighbors to each other. To actually be more precise, protons that are 2, 3 or sometimes even 4 bonds apart may show these cross-peaks. A cross-peak above the diagonal, for example, represents the diagonal peak which is directly below the cross-peak, and the other diagonal, which peak is directly to the right of the cross-peak. COSY is very useful when the multiplets overlap or when extensive second-order coupling complicates the one-dimensional spectrum, or when the peaks show similar coupling constants, so based on the coupling constant, it couldn't be decided which pair of peaks belong to the neighboring protons. Just quickly a few words about the pulse sequence. The simplest COSY sequence consists of a 90-degree RF pulse, which is indicated right here. Pi per 2 means that it's a 90-degree pulse. This is followed by the specific evolution time, which we will call T1, which is actually incremented during the experiment, usually by the power of 2. So for example, there are 128 incrementations. And this is followed by a second 90-degree pulse, which is indicated here. And finally, there is an acquisition time. This is the time when the FID is acquired. The correlation spectroscopy, or COSY NMR experiment, is a proton-detected two-dimensional experiment. Of course, because it's homonuclear, so it has to be proton-detected. There is no other isotope involved. But that is why the sensitivity is rather high, even though because of the T1 evolution time, which is incremented n times, it takes longer to acquire it than to acquire a one-dimensional spectrum. The magnitude of the couplings affects the peak intensity. For small couplings, such as 4-bond couplings, or 3-bond couplings where the dihedral angle is near 90 degrees, the peak intensity will be low. Actually, there are many variants of the COSY sequence, the most popular being DQF COSY, where DQF stands for double quantum filtered. But it is not the scope of this video, however, to introduce these variants in detail. Instead, let's look at a few examples to get the gist of it. Here you can see ethyl acetate and its simulated one-dimensional spectrum. It's very easy to assign the peaks to the given protons. This methyl group here next to the carbonyl carbon must be a singlet, as there are no neighboring protons. So this must be the peak at 2.05 ppm. We have an ethyl group next to the oxygen atom. We expect the methylene group to be at somewhere around 4 ppm and to be a quartet, so here it is. And the methylene group must split the signal of the methyl group into a triplet, and this signal should be somewhere around 1 ppm, so here we are. This signal must belong to the methyl group. In this case, of course, we don't need a COSY spectrum to decide which signals belong to neighboring protons, because we only have 2 signals which show splitting, and it's pretty obvious to assign these signals. But let's see the COSY spectrum as a very easy example. Here we go. So you can see that all the peaks can be seen on the diagonal, even the singlet one. And you can see the cross peaks between the triplet and the quartet, above the diagonal and below the diagonal. Actually, the coordinates of these cross peaks are 4.1 and 1.15 and 1.15 and 4.1. So the x and y coordinates are actually just switched. These cross peaks show us that the two signals belong to two protons or two groups of protons which are neighbors to each other, in other words, which are J-coupled to each other. In this case, this is the methyl and the methylene group. There is another type of COSY experiment which is called DQF or double quantum filtered COSY, and in that case there wouldn't be a signal of the singlet methyl group on the diagonal, because in this case all the signals of the singlets are filtered out. We will talk about this sequence in another video, but you should know about that in the case of the DQF COSY you won't see a singlet on the diagonal. Here is another example, a very similar molecule, ethyl propionate. In this case we can differentiate between two kind of ethyl groups, one next to the carbonyl carbon and one next to the oxygen atom. In both cases we expect a triplet for the methyl group and a quartet for the methylene group. And we can see them on the one-dimensional spectrum, and it's very easy to assign the peak at 4.1 to the methylene group which is next to the oxygen atom, and of course it's very easy to assign the other quartet which belongs to the other methylene group, but it wouldn't be that easy to decide which triplet belongs to which methyl group. And in this case, let's say that the coupling constant is the same in both cases, so actually every multiplet shows a somewhat around 8 Hz coupling. Based on the coupling constant, we can't really decide which triplet belongs to which methyl group. So let's see the COSY spectrum to decide. Again, we can see all the 4 peaks on the diagonal. So let's start from 4.1 on the diagonal, and we can see that we have the cross peak with the triplet at 1.15 ppm. So based on the COSY spectrum, we can assign the peak at 1.15 ppm to the methyl group here. And we can see that there are cross peaks between the peaks at 2.25 and 1.05. So we can see that these are again neighbors to each other. Again, this was still a very simplified, a very easy example. Probably we could have figured it out without the COSY spectrum, but I think this example can nicely demonstrate how useful the COSY spectrum can be. And let's check last example. In this case, actually, just based on the multiplicities, we could assign all the peaks to 4-hydroxybutanol, but I would like to show you how the COSY spectrum looks like in this case. We would expect a triplet for the formyl proton here. The methylene group next to the carbonyl carbon should be a triplet because it has another methylene group as a neighbor. This should be a triplet of triplets, or maybe it's a little bit more simplified if the coupling constants with these two methylene groups are somewhat around the same. And then comes a last methylene group which is next to a hydroxyl group. This should be again a triplet. Usually you can see a coupling with an OH or an exchangeable proton. Let's see the COSY spectrum. Here we go. So we can start from the formyl proton at around 9.6. And actually this is a really nice example because you can see how you can jump along the chain with the help of the COSY spectrum. As I said, let's start from the diagonal signal which belongs to the formyl proton, and let's see with what other peaks it has a cross peak. We can see that we have a cross peak at 2.6 ppm here, so we can jump here and from here to the diagonal. The cross peak means that this peak must belong to the neighbor of the formyl proton, so this methylene group here. And then we can go further. Let's see what's on the right of this diagonal. We see a cross peak with the peak at around 1.9 ppm. So this must be, again, the neighbor of the methylene group, the other methylene group, which can be seen here. And then we can jump to the diagonal again and see with which other peaks it has a cross peak. Of course, we expect that there is a cross peak with the signal at 2.6 ppm, because we've seen this cross peak, only that it was below the diagonal, so this is its pair. But we can see another cross peak at 3.3 ppm. This must belong to the last methylene group, which is next to the oxygen atom, as actually we would expect it based on the chemical shift. So you can see how we can jump through the chain based on the COSY experiment and how we can assign the peaks based on this experiment to the structure. Of course, there are way more complicated and complex examples when there are, for example, overlapping signals or way more signals than in these examples in this video. And the more complicated the proton spectrum is, the more useful the COSY spectrum can be. But there are other very useful two-dimensional experiments which can provide further help to elucidate the structure. So let's talk about these techniques in the upcoming videos.